We are in the last part of application of definite integral where we observe the problem 6. Find the area bounded by the circle x square plus y square equals to 4 and the straight line y equals to x in the first quadrant and x axis. So if we consider the equation of the circle first, which is denoted by 1, obviously can be expressed as x minus 0 whole square plus y minus 0 whole square, that equals to 2 square. So which denotes this is an equation of the circle having center at origin, and radius is 2. So OA is the radius of the circle, which is simply 2, and center here O is 0 0 and OA the radius of the circle is 2, so that the coordinates of the point A is obviously 2 0, since A is a point on the x axis. Now if we consider the straight line on the other hand, if we consider the straight line y equals to x, which denotes the straight line passing through the origin, and we have to find the area bounded by the circle and this straight line in the first quadrant, that is in x axis. So if we want to find the area, first of all our reduction is to find the points of intersection between the circle and the straight line first. Consider this equation as first equation and the given straight line be the second, y equals to x be the second equation. If we solve these two, what we get? Substitute here in the equation 1 x square plus y square equals to 4, y equals to x, so that we get it as x square plus x square equals to 4, or twice x square equals to 4, which gives x square equals to 2, and finally x equals to plus minus root 2. Not only that, when we substitute x equals to root 2, we get y equals to root 2, and again when we substitute x equals to minus root 2, we get y equals to also minus root 2. So this gives the 2 points of intersection between the straight line y equals to x and the circle x square plus y square equals to 4. What are they? In figure, P is obviously root 2 comma root 2 is one of the points of intersection, and Q is minus root 2 comma minus root 2 is the other point of intersection. So we get these two. Now if we consider the area of the circle, area bounded by the circle and the straight line y equals to x in the first quadrant. So here we observe here the shaded region is the required area bounded by the circle and the straight line in the first quadrant. First quadrant means in this area, x axis, y axis. Here we observe the shaded region is the required area, and if we distinguish the total area by two parts, one from O to B and other from B to A, and here we observe first of all the area of the triangle OBP and the other the curvilinear area BPAB. These are the two areas. So we write in this way, required area that we have to find, required area is equals to what? That means here inside the box we can represent in this way. in order to understand the part. First of all, the horizontal line area OBP, and the other is the graphical box. These are the two first part. So first from O to B and the other from B to A. And if we consider in integration form, they are from 0 to root 2. Since the point P is root 2, that means OBBP, the abscissa is root 2, OB is root 2 and PP is also root 2. So that 0 to root 2 y dx where y equals to x, it should be mentioned where y equals to x, and plus from B to A, that is root 2 to 2 y dx x square plus y square equals to 4, where x square plus y square equals to 4. Now the integration. First of all, substitute all the results. 0 to root 2 y. In place of y, we have to substitute x dx plus root 2 to 2 y means 4 minus x square in this place. Since y, if we calculate here, we get y square equals to 4 minus x square, and which implies the value of y as simply square root of 4 minus x square. Square root of 4 minus x square whole dx. Both the integrand is known to us, so that we can proceed forward, and usually x square by 2 from 0 to root 2. These are the upper and lower limits, and here if we apply the formula inside square root, a square minus x square whole dx, that gives x into square root of 4 minus x square whole divided by 2 plus a square by 2 means here a square is 4 by 2 sine inverse x by a, that means x by 2 from root 2 to 2. Here these are the upper limit and lower limit. Now it is the best time to substitute both the limits in both the cases. That is here root 2 whole square means 2 by 2, which gives actually 1, minus 0 square by 2, that gives actually 0. And the next part is, if we substitute the upper limit first, 2 into 4 minus 2 square, that gives simply 0, plus 4 by 2 means 2 into sine inverse x by 2. In place of x, we have to substitute 2 first, that is sine inverse 2 by 2, which gives 1. Sine inverse 1, we know that the value of sine 90 degree or sine pi by 2 is obviously 1, so that we have to substitute sine inverse 1 is simply pi by 2 minus, substitute the lower limit then, root 2 into 4 minus root 2 whole square means 4 minus 2, root 2 into 2 gives product 1 2, so 2 by 2, finally it gives 1, minus 4 by 2 means simply 2, and the other part is sine inverse root 2 by 2, simply 1 by root 2. Now this is simply 1 plus 2 into pi by 2 means pi, minus 1 minus 2 into sine inverse 1 by root 2. Since in inverse circular function we have the result, since sine pi by 4 means sine 45 degree, that gives the result 1 by 2 1 by root 2, so that sine inverse 1 by root 2 is simply pi by 4. So if we simplify here, we get these two are same but opposite in sign, so cancels each other. that is pi minus pi by 2, and finally we get the result as pi by 2. Since this is the area, so it should have some unit, maybe denoted by pi by 2 square unit. So we get the finally the area of the portion in our figure, the shaded region. So we are concluding here the basic part of total integration or integral calculus, in which we observe in subunit 1 3.1. This belongs to the part unit 3, which is integral calculus, and in subunit 3.1 we are considering there the indefinite integral, and here also there are so many types and methods of substitution, integration by parts, and so on. And when we consider the subunit 3.2, in which we observe the part definite integral, and so many formulae are there, and we proceed in another manner to get the integration. And after that we consider the part application of definite integral in subunit 3.2, and that concludes the part. And we have to discuss next classes about another application of integral calculus that may be noted as the differential equation, in which we have to first of all we have to discuss about the first order differential equation and so on.